Alright, hello boys and girls. So today we'll be looking at examples of the axiomatic definition in use. And so for that, just give me a minute. Okay, so for that, I'll be taking some of your favorite questions from high school and I'll be solving them using the axiomatic approach to probability. Okay, so let's look at the question now. Given a coin, which can either give heads or tails, that coin is tossed 4 times, and now your goal is to find the probability of 3 tails among those 4 tosses. So 3 out of 4 tosses should give you tails. Find the probability of that. Okay, cool. So the first thing is we have to create a probability space, omega fp. Now omega is the sample space which basically has all of the outcomes that are possible in one trial. And by one trial, I mean tossing a coin 4 times. So how will I write down or encode the info about one trial? So simple thing, I can encode all that in a list. So the list will contain the outcome of the first toss, second toss, third toss, fourth toss. Okay, and I'll write it down as a vector. And so this way, each of this, the T0 can take either heads or tails. Similarly, T1, T2, T3 as well. They can, all of those can take heads or tails. And so the sample space for your experiment, it basically becomes all the T vectors such that their components are heads or tails, right? That's the sample space. And what we'll be doing is trying to assign a probability measure for each of these events, each of these elementary events. Next, if we have assigned a probability measure for such elementary events, so we can also assign the probabilities, or we can at least find the probabilities of any subset of omega that way, right? Any subset of the sample space is basically a union of those elementary events, right? And so the event space, that is the collection of events that are possible, is all the possible subsets of omega. And before I proceed any further, how many possible outcomes are there in omega? Take a while to think about it. And the answer is 16. Why? Because each of these can take 2 values, heads or tails, and there are 4 of them. How many possible combinations? 2 raised to 4, 16. Simple combinatorics. Okay. Now, how many possible subsets of omega are there? Yeah, I jumped from one question to another much more complicated question, right? Yeah, how many subsets of omega are there? How many events are there? So for those of you who know your set theory, there is 2 raised to 16. I'm not going to derive where it came from, but there are 2 raised to 16 possible events in this case. Now, how will I create a probability measure? Okay, now the way to create a probability measure in this case is, I mean, it's not necessary that you create it this way only. So there is no info given on the nature of the coin, and the axiom only tells you what the probability measure should obey. It does not tell you how to construct a probability measure. It just tells you how that probability measure should behave. It does not tell you what it should look like, who it is, what sort of functional form it should take. All those things, that is up to us. And we just have to ensure that whatever we construct, in this case over here I have done it, whatever this is, it should follow those 3 axioms, nothing else. Okay. So consider this p function. Actually, I'll name it something else. It's actually going to be, okay, so for no confusion, I'm calling that thing as f instead of p. Okay, now assume for one single component I have something called a f function. Okay, so that f function will take either heads or tails, and for that it will spit out p and q, right? So it will it will take in heads or tails. For tails it will give you p, and for heads it will give you q. Now that's the f function. From that, I'm creating the probability measure for one single outcome as the product of the individual f functions for each of these components. Okay, do you understand? Okay, pause and ponder over here what I've done. This f function, it will take in heads or tails, give you p or q, and the probability measure that I'm using is basically a product of individual f functions of the components of your outcome. And now you might recognize this to be a bit familiar with a coin toss, in which single toss has probability p and q, right? Here, yeah, I mean, we can eventually prove that this single toss has a probability of p and q, that is the probability of heads and tails comes out to be p and q. But I haven't said anything about p plus q being equal to 1. That is something we'll prove later on, that this sort of stuff will happen. Okay. And now I'll design how my event will look. My event is basically any t vector in which 3 out of the 4 elements, 3 out of the 4 components are tails. For a single trial with 3 tails and 1 heads, the probability of that using this probability measure will be p cube times q, right? Because 3 tails, so 3 p's being multiplied, that's p cube. There is 1 heads for which there is a q, and so p cubes times q. Now this is valid for every 3 tails 1 heads outcome. How many of them are there? How many 3 tails 1 heads outcomes are possible in the sample space? There are 4 of them possible. It's TT, TH, TT, HT, TH, TT, and there is a HTTT. So there are 4 of them. And by simple combinatorics, people can also say that it's 4C3, the number of possible outcomes there, and that comes out to be 4. So the probability of having 3 tails out of the 4 tosses is 4 times p cube times q. Yes, it is there. Single outcome with 3 tails 1 heads, that's p cube q. For 4 of them, which are all mutually exclusive events, by the way, that's why I'm able to add them like this. Third axiom, the probability of your 3 out of 4 being tails comes out to be 4 times p cube times q. Now the big question is p plus q equal to 1. I haven't said that it is 1. I just constructed some weird probability measure that came into my mind. Okay, I didn't assume that p plus q was 1, but is it 1? Let's find out. Now consider these events. Okay, x0 is basically 0 tails 4 heads, x1 is 1 tail 3 heads, x2 2 tails 2 heads, and similarly going on. Now all these events, observe that they're all mutually exclusive. Okay, so you cannot have 0 tails and 1 tails in the same trial. That's just not possible. So all of these are mutually exclusive events, and the union of all of these gives you the sample space. Fair enough. So the sample space will contain 0 tails, 1 tails, 2 tails, 3 tails, 4 tails, right? And so their union is the sample space, and adding the probabilities of all these events hence should be 1. Now what is the probability of each of these events? Now if I take a generic xi, that is I tails, so there will, for each of the tails I will have a p, so p raised to I. For 4 minus I heads, each of the heads I'll have a q minus I, and so I'll also have this 4ci coefficient, because that's the number of possible ways to arrange I tails and 4 minus I heads. And so for each generic event xi, this is the probability. Now if I add all of these probabilities, I equal to 0, 1, 2, 3, 4, if I consider all these events, adding their probabilities, I'll get a binomial series. Okay, pause and ponder upon that. I'll get a binomial series with p plus q raised to 4, and that is being equal to 1. So if p plus q raised to 4 is 1, then obviously p plus q is equal to 1, because p plus q cannot be minus 1. I mean, what we have considered is that p and q are greater than or equal to 0, and we don't need to assume that actually if we take a measure like this, you can actually prove that p and q are greater than 0. Okay, so how you can prove p and q are greater than 0? Well, simple. I mean, just find out what is the probability of the first element being a head. Rest elements can be whatever they want. Just find out what's the probability of first event, first component, first toss giving you a head or a tails. Find out what that is. The other events can, go to hell. We don't care about what they are. So if you notice, if t is t0, t1, t3, probability of t0 being heads is basically q, and t0 being a tails is basically p. And since the probability of events in the sample space, p and q must be greater than or equal to 0. And if p and q are greater than or equal to 0, they cannot be summed up to -1. So hence they have to be summed up to 1, and we have officially proved that is p plus q that I just brought out of the wind from somewhere, they sum up to 1 by the axioms. Okay, so in the next video I'll go through another example, and in that example I'll take a slightly more difficult problem and introduce a very clever way to solve it, and that also I'll do it with the axioms. Okay, see you then.